Okay, we've analyzed 3 different possible improvements to the hardware and their effect on CPI and therefore their effect on performance. Let's move into some other material now. Let's go on to the next area, which looks at number of instructions and the effect that a compiler can have on performance. Now, a compiler is a software tool. How can a compiler affect the performance of a computer? Well, I think if you realize the number of instructions will be generated by the compiler, and the type of instructions, will they be fast little ones with short CPIs or long slow ones with long CPIs, you realize the compiler will affect 2 out of the 3 performance components. It won't affect the clock cycle time, but it will affect the CPI by the instruction mix that it chooses, and it will affect the number of instructions by the code that it generates. So, a compiler designer is trying to decide between 2 code sequences for a particular machine. In other words, given this high-level block, how will I turn that into assembly and machine code? Could do it this way, could do it that way, given a target architecture. Given machine means the ISA is fixed. Based on the hardware implementation, there's 3 different classes of instructions. Class A, Class B, Class C. Last time there were 4 classes: ALU, load, store, and branch jump class. All right, this time there's 3 classes, and they just have names. And the 3 classes require 1 cycle for Class A, 2 cycles for Class B, and 3 cycles for Class C. So that means that if you generate a lot of Class C instructions, you'll have a high CPI. If you generate a lot of Class A instructions, you'll have a low CPI. If you generate a lot of Class B instructions, you'll have a middle CPI. Okay, you with me so far? So this is the compiler's choice in how it will implement given a machine. But of course, performance means a program as it runs on a machine. So with a given clock cycle time, on a given ISA, a given program which has been compiled into a given set of machine language instructions. So you realize, oh, compiler is part of the overall performance picture, isn't it? Let's see how that works here. The first code sequence that the compiler is thinking about doing has got 5 instructions. And the 5 instructions are 2 Class A, 1 Class B, 2 Class C. I think you could figure out the CPI right now. The second sequence has 6 instructions. So it's got a bigger I, but 4 of Class A, 1 of Class B, and 1 of Class C. Which sequence is going to be faster, and by how much? What is the CPI going to be for each sequence? Okay. Can you tell me if time is equal to I times CPI times clock cycle time? The compiler designer is playing with 2 different versions of this. It's going to do it that way, it's going to do it that way. Obviously, this is not going to change because the machine doesn't change. The question is, what is I times CPI? Instructions per program multiplied by cycles per instruction. What's that? Cycles for the program. Okay, or in this case, piece of the program. Can anybody tell me how many cycles this first sequence is? How many cycles is it? 10? How'd you get that so fast? 2 A's is 2 cycles. 1 B is 2 more, that's 4. And 2 C's is 2 times 3, 6 more. Yeah, you're right, it's 10. So for the first way he's thinking of doing it, it's 10 cycles. Or another way to say it is, I is 5, and what's CPI? 2.0. Okay? Can we find out why it's 2.0? 2 times 2 instructions out of 5. So that's the frequency multiplied by number of cycles is 1. What's the frequency of the B-type instructions? 1 out of 5. And its number of cycles are 2 each. And the third type of instruction, it's 2 out of the 5. So it's again 40%. And how many cycles are they? 3 each. So can everybody see here that 40% of the instructions are 1 cycle, and 20% of the instructions are 2 cycles, and 40% of the instructions are 3 cycles. What's that add up to? 2.0. So the formula way of calculating it and number of cycles divided by number of instructions to give cycles per instruction, that works too. So there we go. 5 times 2.0 is 10 cycles. Let's look at the second one. How many cycles is the second sequence? 4 of A is 4 cycles. 1 of B is 2 more, that makes me 6. 1 of C is 3 more, makes 9. So the second one is only 9 cycles. For 6 instructions. I was 6 instructions, therefore my CPI is equal to 9 cycles, 6 instructions, cycles per instruction, yeah, 1.5. Can we figure that out using the formula approach? Okay, I've got 6 cycles, so 4 out of 6 is the frequency of the type A instructions, and they're 1 cycle each. 1 out of 6 times 2 is the frequency of the type B, and 1 out of 6 multiplied by 3 is the frequency and the contribution of type C. So what do we get here? 4 out of 6, 0.666. 2 out of 6, 0.333. 3 out of 6, 0.5. When we add all that up, and that's 1.5, sure enough. Just like we said, 1.5. Okay, so we can calculate it that way. We can calculate it this way. Now here we go. The question is, which sequence will be faster? 10 cycle sequence or 9 cycle sequence? Faster. This is same times 10. This is same times 9. What's going to give me a smaller time? Yeah, the 9 cycle sequence. Even though it has 6 instructions and this one has 5 instructions. How can 6 instructions be faster than 5 instructions? Because it has a CPI that's significantly lower, 1.5 instead of 2. What did the second compiler sequence do? What did it do? It heavily concentrated on the short, fast instructions and tried not to use the slower, big instructions. What did the first compiler sequence do? It scattered its usage, including some very slow instructions that take 3 cycles each. Do you see the difference? Less instructions doesn't mean faster. Less cycles doesn't mean faster unless the clock is the same in both. But if the clock is the same, less cycles means faster. Less instructions doesn't mean faster. Smaller CPI by itself doesn't mean faster. Total number of cycles might mean faster if the clock cycle time is the same. In this case, the clock cycle time is the same. Any questions about this example? All of these examples are designed to do what? Sizleri şaşırtmak için. They're all chosen to shake you up and say, what? That's impossible. Clock speed doesn't directly proportion to performance. Number of instructions isn't related to performance. Yes, related, but it's not the same thing. I said that in the introductory lesson the other time. Performance doesn't equal I. It doesn't equal CPI. It doesn't equal clock cycle time. What does performance equal? The inverse of time, which is the product of 3 things, and they're all important. Okay, now, any questions about this? Okay, now, which is the CPI for each sequence? Well, we've calculated it. We also found a different way. 2.0 and 1.5. Does this mean this is going to be faster? No, not by itself. Does this mean this is going to be faster? No, not by itself. Does this mean it's going to be faster? No, not by itself, unless these stay the same. If they stay the same, then this is enough information. 10, 9, we know the winner. Okay? Any questions about this? Any questions at all about this? I'm trying to shake you up from trusting foolish things. I'm trying to get you on a new, strong foundation where you trust truth and you don't trust your intuition or your, kind of Varsayamlar or your old perspective. That's a little bit hard to do. You have to be willing to let go and say, okay, I see what he's saying. I'm not going to continue to rely on things that I thought because I've now understood they were incomplete or partial or even foolish. Or they were misconceptions or they were Varsayam or Onyarga, and they're not correct anymore. You've got to be willing to change your perspective if you're going to be a learner, a lifelong learner, if you're going to be a person that keeps up with the modern world. You cannot say, I know it never changes, I'm just going to hang on to this. Inflexibility is death in a fast-changing career like this. Okay, let's move on. Now, let's talk Java. There's an application program that's been written in Java and it runs in 15 seconds and that's too slow. Oh, too slow. Slow Java. So what are we going to do? It runs on a desktop processor. We got a new Java compiler. Yeah, we're going to speed that baby up. We didn't change the hardware at all. Same machine, no new investment. Just get a better compiler. Does anybody remember back where we compared Java and C with optimization level 0, 1, and 2? No optimization. Java with just-in-time pre-compiling. Remember all that stuff? Yeah, Java is slow, but you can speed it up. How do you speed it up? Much better. Compilation. Don't interpret. Interpreted languages are wicked slow. Java is like BASIC. It's terribly, terribly slow unless you compile. Now, a new Java compiler is released that only requires 6/10 as many instructions as the old compiler. So what does that mean? I is now a lot less. Unfortunately, CPI went up. So we got I down, oh good, that's going to help our time, but CPI went up, oh bad, that's going to hurt our time, isn't it? See what's happening here? It happened before in a different example. This one got better, but that one got worse. Remember what that was? Clock cycle time went up, but CPI down, yay, CPI went up, boo. All right, same thing here, only it's I on CPI. It's almost never that you can just change one thing and have no effect on the others. So we're talking about compiling here. The last two examples are trying to teach you that compilers are such an important part of the performance overall of your system. Choose a good compiler, you get better performance than choosing a bad compiler. Turn on optimization, you get better performance than if you turn it off. Choose an interpreted language, you get worse performance than a compiled language. Choose the newest improved compiler, you get better performance than the old compiler, but you'll have to pay a little more money. They don't give compilers away for free. All right, so now the question is, how fast can we expect the application to run using this new compiler? So what do we know? Clock cycle doesn't change. CPI changed. I changed. Overall time changed. We know the number of instructions, old and new. We know the CPI, old and new. We know the old time. What are we trying to find? New time. Okay. So turn to your partner and in 2 minutes solve this middle school single equation algebraic problem. Okay? Turn to your partner and in 2 minutes solve this middle school mathematical level single equation, single unknown problem is applied to computer engineering. And if your partner isn't able to, tell him your little brother or sister can, and they ought to be ashamed to not be able to do a single equation, single unknown algebra problem at the university level in an engineering department. I'm sorry. Raise your hand if you found that the new compiler runs this in 10 seconds. Raise your hand if you found that it runs it in 10 seconds. If you found that, you got the right answer. It runs it in 10 seconds. So therefore, what's the performance increase? What's the performance increase? 1.5, 15, which is the old time, divided by 10, which is the new time, 1.5. How do we get 10 seconds? Would you like to explain? You raised your hand. How'd you get 10 seconds? Yeah.
We first get the old time, this 15.
Old time's 15.
Yeah. Then the instructions are reduced by 6 over 10.
Okay.
Multiply.
Oops. Oops. Did anybody start like this? 10 is equal to I old times CPI old times clock cycle time? 15, sorry. Thank you. And then write, we don't know is equal to, here we go, 0.6 I old times CPI multiplied by 1.1 multiplied by clock cycle time. Okay, now, watch this. Let's make a ratio. Okay. This equals bye-bye, bye-bye, bye-bye. So what do we got? 15 divided by what the thing we're looking for is equal to 1 over 0.66. Did anybody do something like that? Okay, so what do we got? We have a 15, we have a 0.66, and we're looking for 1. So one equation, one unknown. That's a really easy way to do it. Write the equation for the old time, write the equation for the new time, make them in a ratio over each other. Yeah?
We also did time, but it says it increases the CPI by 1.1. Yani it makes it 2 point.
No. No. Factor of. Yani eski CPI çarpı 1.1. And that's the only meaning that we can have because we don't know. Oh, I see what you did. You CPI plus 1.1. No, it's not. I mean, it would be better if it said factor. Yeah, hoc variorum. Okay, did anybody else get confused like that on interpreting the specification? In any way, not just that. Anyway, you had trouble understanding those words and how to put them into a mathematical model. Okay, so hoc variorum could have been clearer, but at least you should have been able to model it and then do the middle school math. Tamam. Okay, well, let's go on. So we've had 2 in a row showing the compiler has a big effect on performance. Now, when we design the instruction set architecture, when we design the machine, there's some trade-offs, and this is what you're talking about. It'd be great to have a fast clock. It'd be great to have a small CPI, and it'd be great to execute few instructions. That'd be lovely. Then we'd have fast performance. But you know what? Those often pull against each other. I've showed examples where you're trying to do something with one. That last example was another one here. Instructions goes down, but CPI goes up. They're pulling against each other. It's a trade-off. You're trying to design a place where the overall product is minimum, but not for any one individual factor. Okay, now, there's 2 basic architectural approaches in designing computer organizations these days. One is called RISC, Reduced Instruction Set Computer, and one is called CISC, Complex Instruction Set Computer. A complex instruction set means it has complex instructions, powerful instructions that execute in many clock cycles, but you'll not need many of them because they're powerful and each one does a lot. On the other hand, in a RISC, a reduced instruction set machine says, get rid of the complex instructions, only have simple instructions. You're going to need a lot more of them to accomplish the same tasks, but they'll all be very simple. So each instruction does just one simple operation. It's easy to implement, so the CPI is going to stay really low because they're all simple and fast, maybe close to 1. It's going to take more units. It's going to allow, because the architecture small, control is small, you're going to allow more units on the chip and we can run at a faster clock rate. But it's going to take many more instructions for a program because they're all small and atomic and it takes a lot of them. The CISC approach is get powerful instructions which do a lot of work, but they take many cycles each, but you don't need many of them for the program. But the cycle time is going to be long because they're complicated instructions. Okay, that's the idea here. So 2 different approaches architecturally. Now, this MIPS doesn't mean the MIPS architecture that we've studied. It means million instructions per second. And that's a common measurement tool in processor performance, and that's why this MIPS took the name. Okay? That already existed. Oh, let's use a name that already exists. So 1 MIPS means a particular processor architecture, but this MIPS means million instructions per second. It's a measure of how fast the instructions are executing. Let me ask you a question. Do you think that RISC will have a higher instruction per second rate or CISC? Yeah, because they're simple and little and you're going to get a lot more done fast. So this will have a higher MIPS, this will have a lower MIPS. Question is MIPS important? Is it useful? What does it teach us? Let's go have a look. 2 different compilers are being tested for a 4 gigahertz machine with 3 different classes of instruction, A, B, and C. So here we go again. ISA is fixed. We got 2 different compilers. One generates this set of instructions with this set of CPI. Other one generates a different set. Both compilers are used to produce code for a large piece of software. And there's class A, B, and C, and they each take 1, 2, and 3 cycles to make it simple. The first compiler's code generates 5 billion class A instructions, 1 billion class B instructions, and 1 billion class C instructions. The second compiler's code, to do the same high-level thing, generates 10 billion class A instructions, 1 billion class B instructions, and 1 billion class C instructions. Which sequence will be faster according to execution time? Don't have to even put your pencil on the paper. Is this going to be faster or is this going to be faster? A. Why is it faster? because they both have the same number of Class C instructions, same number of Class B instructions, and their only difference is Class A instructions. This has more, this has less, therefore this is less. Less total cycles for a fixed, this is going to be faster, clearly faster in time. Question is, what if we measure million instructions per second? All right, now that one's going to take some calculation. So what I'm going to do is do it on the board, show you some surprising things. MIPS, as I said, is a commonly used measure of performance. What would you think if the first compiler's code ran faster, but the second compiler's code had a higher MIPS? If this is, 1800 MIPS, and this is 1400 MIPS, you would say, oh, it's got a higher MIPS. Does that mean it has higher performance? No, because we just finished saying this is going to run faster. This has higher performance. So what do you conclude? MIPS is not a reliable measure of performance. Just like I is not, CPI is not, clock cycle time is not. Do you see what I'm doing? I'm setting up all the candidates and showing nope, no good, nope, no good, nope, no good. All of these things that people trust are not reliable measures of performance. Let's see how this one works. I think you'll be, well, you won't be shocked because I already let the cat out of the bag here. But let's just see how it works. All right, if we calculate the number of cycles for the first compiler's code, so cycles for 1 and cycles for 2, and then we multiply by the clock cycle time. What is the clock cycle time for 4 gigahertz? 1/4 of a nanosecond. Is that okay? 1 gigahertz, 1 nanosecond. 4 gigahertz, 1/4 of it. Would that's all right? Can anybody give this in a little bit more, scientific form? How would you say that? 1/4 of a nanosecond is not what we say. What do we say? 250 picoseconds. Right, after nano, 1 becomes pico, factor of 1,000. So 250 picoseconds, but this is nice. Let's leave it like that. Okay, and then this is going to be multiplied by the same thing because the machines are the same. So what we really need to do, and this is going to give me time of machine 1, this is going to give me time of machine 2. Right? How many cycles is that first set of code? 5 billion. 2 billion more is 7 billion. 3 billion more is 10 billion. Right? So number of cycles is 10 times 10 to the 9th. Agreed? All right, here we go. Second one. 10 billion each taking 1, and then 1 billion each taking 2, so I'm up to 12 billion, and 1 billion more each taking 3, so I'm up to 15 billion. So the second sequence is 15 times 10 to the 9th. So now we can figure out the time. What's the time of the first one? How many seconds? 2.5 seconds. Great. How about the second one? $15 divided by 2 is 7.5. 7.5 divided by 2 is 3.75 seconds. So clearly, just as we said, this has less cycles, so therefore it's faster. 2.5 seconds, 3.75 seconds. Now let's find million instructions per second. So MIPS of number 1 and MIPS of number 2 is what? Instructions over seconds. 2.5 seconds. The other one's over 3.75 seconds. How many instructions did code sequence 1 execute? 5, 6, 7 billion. Okay? 7 times billion would be 10 to the 9th. But I'm trying to not measure instructions per second. I'm trying to measure million instructions per second. So I'll go 10 to the 3rd, right? Because this million means 10 to the 6th already. Okay? How about over here? How many instructions did this execute? 10, 11, 12 billion. So we got 12 times 10 to the 3rd divided by that. Okay, I'm not real good at this kind of non-trivial mental math, but I can tell you that's almost 3. So let's call it 2.8, 2.8, but times 1,000, so 2,800 MIPS for that one. 12 divided by 4 is 3, but this is a little bit less than 4, so it's a little bit over 3. Well, let's call it 3.2. Thank you very much. 3.2 times 10 to the 3rd, so 3,200. Well, what do you know? This has a bigger MIPS, but it's slower. And this has got a smaller MIPS, and it's faster. So is MIPS a reliable indicator or measure of performance? Absolutely not. Absolutely not. So when the salesman comes and says to you, our machine executes 48 billion MIPS, and you say, well, we do floating point. Oh, well, then it executes, 32,000 floating point instructions per picosecond or whatever. What are you going to tell them? Well, that's very nice, sir. Thank you very much. But I'm really interested not in false measurements of performance, which just try to fool me and my boss to spending our hard-earned money on your machines. I'd actually like to know how long in time does it take for this program that I'm highly interested in to execute on your machine. Blah, blah, blah. We don't talk about time, We talk about CPI and clock cycle. We got a great clock cycle rate. We got a high MIPS. Sir, I'm interested in time. I want to know how long my program compiled by this compilation runs on your machine. Okay? Right? Okay, sorry, this is the world, the real world. It's full of fuzz and hype and exaggeration and even outright lies. You know what? There's a lot of people that want to separate you from your money. They want it to go far away. And you've worked so hard to earn your money. Your company's worked so hard to market your products and earn your profit. And you don't want to give it away unless it's really necessary. All right? Really necessary. This is serious talk, I'm telling you. Okay, so we've seen that these do not agree. Performance and time doesn't necessarily have anything to do with MIPS. All right, so MIPS is a pitfall. It's not a reliable performance metric. The instruction rate versus the capabilities of the instructions. Can anybody say why this seemed to have such a high MIPS? Because it's executing a lot of really weak instructions. Okay, so of course it has a high MIPS. The ratio of Class A instructions in this is much higher than the ratio of Class A instructions in this. It doesn't mean that we get more computing done. In fact, we got less computing done in the same amount of time here, right? Because the instructions were all tiny and little. So this says it's the capability of the instructions, not just how fast you run them through the machine. Secondly, is different computers have different instruction sets with different capabilities. Yeah, MIPS, RISC and CISC are completely different. So saying, I've got a RISC machine that has an enormous MIPS, okay, yeah, but what's the actual computing throughput or performance in time? That's what matters. MIPS varies even between differing programs on the same machine. Hello? This is the same machine. We didn't even change machines or clock rates. We just changed the compilation. So, and different programs will have different MIPS. In other words, run the same program, program A on your machine through your compiler. Run program B on your machine, you'll find the MIPS changed. Because program A might have executed more complex instructions and B might have executed more simple instructions. All right, now, here's the summary. We've talked and talked and talked. What affects performance? Well, what I want you to see is the three factors are instruction count, CPI, and clock rate, right? It's the product of all of those three that make for time. What affects instruction count? Program does. Write a good algorithm, you'll have a lot less instructions that have to run and execute than if you write a bad algorithm. Order of n is better than order of n squared. Order of log n is better than both. N log n is better than n squared, but it's worse than n, right? All that algorithm stuff, the program you write, including the language that you choose. The compiler, we've seen clearly how compilers can have a big effect on the number of instructions. And even the instruction set architecture. Because if I have an instruction set architecture that offers simple instructions, you're going to have to use a lot of them. If I have an instruction set architecture that offers complicated, powerful instructions, you'll need less of them. So the ISA affects this as well. Those are the things that affect one factor. Now let's look at the next factor, CPI. What affects cycles per instruction? The compiler, because if it chooses a mix of the fast, simple instructions with low cycle count, you're going to get a lower CPI. If it targets more toward the complicated ones, you're going to get a higher CPI because they're slower and take more cycles. Also the instruction set architecture. What's it offering in terms of the mix? Is it offering low CPI instructions or high? And how many cycles for the loads, how many cycles for the stores, how many cycles? Remember, we did some work on reducing the number of cycles by improving the architecture. Okay? Then the organization itself. Intel and AMD both implement the same instruction set architecture, but they got different machines under the hood, and guess what? They have different CPIs. Because Intel's engineers said, let's do it this way, and AMD's engineers said, let's do it this way, and they get a different CPI. Okay, let's go again. Clock rate. What affects clock rate? program doesn't, compiler doesn't, even the ISA doesn't. But once you get into the machine underneath, how you organize your structures, your units, your data paths, your registers and everything, and the technology, what you're switching with, what the actual physical transistors and the circuit layout. So those will affect the clock rate. So if you look at that chart, you'd have to say there's 5 things that are important. Electrical engineering, digital design engineering, computer organization, compilers, and programs and algorithms and programming languages. Wow, that's pretty much the whole spectrum of computer engineering plus, because we don't even go down to here, the technology level. We could, some programs do, but we leave that to electrical engineering. Pretty much the whole thing. A lot of different factors affect performance of programs. Which factor would you say is the single most important factor? The single most important factor?
Technology.
Well, looks to me like technology affects just 1 of the 3. Organization affects 2 of the 3. Compiler affects 2 of the 3. The program and language and algorithm affect 1 of the 3. Instruction set architecture affects 2 of the 3. So I would have to say these are not good candidates because they only affect 1. You might argue between compiler, instruction set architecture, and computer organization as being the one that has the greatest effect because it affects 2 out of the 3 factors. Okay? We could have a debate about that, but I think I'd rather spend our time in another way. But clearly, 5 different factors affect what you're doing here. And remember what we said earlier? We said no smart compiler can make up for a stupid algorithm, right? Yeah. And no whizzy fast technology is going to make up for bad digital design. And no great compiler and program can salvage a suboptimal choice in instruction set architecture. Every one of them is important, but each of them depends on the others for a full performance. So what you're trying overall is to get great programs written in great languages with compilers that turn them into the best assembly and machine code they can, but targeting the best architecture that they can, which is implemented in the best way that it can be on the fastest technology available. That's what we'd like to have for best performance. That way, all 3 of these are the best that they can be. Okay, I hope that's a useful tour through performance. It's actually quite an interesting area, and it's quite comprehensive. It's not just about turning up the clock rate. Oh, wow, look at that baby smoke. We're going fast now. Okay, there's a whole lot more to it than that. If you came into the class today thinking, that's it, performance is about clock rate, and I'm going to overdrive my clock or overclock it or move up to a faster CPU by doubling the gigahertz, I hope you're leaving a lot more sophisticated, a lot more realistic about the factors affecting performance. Now, there's one last thing I'd like to say, and that is about benchmarks. Benchmarks are programs that are standardized and whose performance is measured on an architecture and a hardware realization. So the programs and the compiling of them is standardized, so it's fair. So therefore, if you say, hey, I got a fast new processor, well, let's see how it does against a standard set of benchmark programs. Okay, so it gives a fixed measurement. Those are posted on websites. They're measured by lots of measuring labs. It's kind of a fair test, you might say. Now, the only thing better is your own program, because you say, well, that's very nice. I see a nice list of floating point programs here, but mine's not in the list. I actually don't run these. I run mine. Well, yours is probably pretty close to some of these, but the very best test is to run your own program. But of course, that's a specialized thing. You've got to have the architecture and so on. So people like benchmarks, but performance is measured best by running a real program. So you're going to use programs which either are your workload or they're typical of the expected workload. Do you run a lot of transaction processing? Do you run a lot of web serving? Do you run a lot of real time? Do you run a lot of graphics? Do you run a lot of whatever? Then your benchmark needs to be of that kind of program. Okay? Or typical of the expected class of applications. Is it compiler editor class? Is it scientific application class? Is it graphic class? You want to run benchmarks that are close to what you're really going to be doing. Now there's small benchmarks which are useful in the design stage. Architects and designers run these as tested about performance. They're easy to standardize too, but they can be abused. They're not real programs. big, serious programs are what users need to use for their benchmarks. So SPEC, which is System Performance Evaluation Cooperative, is a group of industry companies in the hardware, software, compiler, language area, which is standardized on a set of real programs and real inputs to those programs, which are going to be a fair and equal test, okay? And they're a valuable indicator of performance and also of compiler technology, but guess what? They can still be abused. And the history of SPEC shows that they've had to stop abuse by weeding out some programs that are vulnerable to special tuning and so on. So these can easily be abused, but if you work hard enough, these can be too. So SPEC's job is to protect a fair set of programs so that you really get a true indication of performance. All right, and if you read the history, you'll find out that sometimes there was a hole, and somebody found the hole and got an unfair advantage. But that's okay. They're continually monitoring it and upgrading it. So that's about all I want to say from this chapter. What I want to do now is give you an assignment. So break back into your teams of 2 or 3, and let's use the rest of the time to work on this.